Good evening. So yes, Deshnan Senthil. Hi Deshnan. All right. So today we are going to discuss some problems based upon gravitation. So let's begin. So here is our first problem. So problem number one: a body weighs 63 Newton on the surface of Earth. What is gravitational force on it due to Earth at the height equal to half of radius of Earth? Okay. So can you solve this problem? All right, so let's note down the given things. A body weighs 63 newtons on surface of Earth. So what is weight of an object? Weight of an object is the gravitational force exerted on the object by Earth. Okay, and how much is that? So it's given that weight, I can write it's equal to gravitational force equals to 63 newtons, and this is on Earth's surface. Okay, so I can write this as mass of the body multiplied by acceleration due to gravity on Earth's surface. Okay, question is what is the gravitational force on it due to the Earth at height equal to half the radius of Earth. So this is on Earth's surface. So we know what is the gravitational force. It is given by F suffix g is g times mass of Earth multiplied by mass of body divided by r squared. Okay, so when body is on Earth's surface, the distance between body and Earth, it is r. Now force due to gravity at some height h, so I will write this as f suffix g h. Okay, g at some h, so it will be equal to gmm divided by r plus h squared. Okay, so this r will change to r plus s, r plus h. Distance between the earth center and that object changes to r plus h. All right, so then what we can do is we can divide this first equation by second equation, and if we divide, what do we get? We get, I will divide second by first one, so f suffix gh divided by f suffix g is equal to what? Gmm over r plus h squared, and dividing by this gmm over r squared is multiplied by its reciprocal, so I will multiply by its reciprocal. Okay, so I will write r squared over gmm. So we can see that this gmm and gmm gets cancelled out, and what we are left with is r divided by r plus h squared. Okay, so it is r over r plus h squared. It is r squared divided by r plus h squared, which I can write like this also. Okay, so then let's take this on next page. So let's add a slide over here. Okay, so now let's substitute value of h. So how much is value of h? It is r by 2. Okay, so we have f suffix gh divided by f suffix g equals to r over r plus r by 2, and we have square of all this. So which can be written as r divided by, this is r plus r by 2, that is 3 by 2 r, so 3 by 2 r, and we have square of all this. Then again we can cancel out r and r from numerator and denominator. So this 2 goes to numerator, so it is 2 by 3 squared, and that's why 2 by 3 squared is 4 by 9. So I will take this fg on other side. So we have f suffix gh equals to 4 by 9 times f suffix g. And now we can substitute the value. So it is 4 by 9 multiplied by the gravitational force on Earth. All right. So then let's move on to the next problem. Next problem is a rocket is fired from Earth toward the sun. Okay, so we have a rocket which is fired from Earth towards sun. At what distance from the Earth center is the gravitational force on the rocket 0? Okay, so let's suppose we have Earth. Okay, so let's suppose this is Earth, and we fire a rocket from here towards sun. Okay, so sun is somewhere over here. And right now the distance between the center of Earth to center of sun, it's something, let's suppose it is r. So yes, okay, so we fire this rocket along this path, and let's suppose our rocket goes at this much distance. I'm very bad at drawing, it's okay. So this is my rocket, it goes at this much distance, and now what happens is the force on this rocket, net force, becomes 0. Okay, so we have to find this distance from, right? So is the question clear? Okay, so then distance of this rocket from Earth center is suppose x, then distance from the center of sun will be r minus x. All right, so now since net force on the rocket becomes 0, the force due to Earth which acts in this direction, this is force on rocket due to Earth. So this force must be equal to what? Force due to the sun. So two forces, the force due to Earth, equal and opposite, and that's why they get cancelled out. Okay, so this is force on rocket due to Earth, this is force on rocket due to sun. Okay, so in magnitude they are same. So what I can say is force on rocket due to Earth is equal to force on rocket due to the sun. Okay, so now we know the formula for gravitational force. So force on rocket due to Earth will be g multiplied by mass of Earth multiplied by mass of rocket, I will call it small m only, divided by distance squared. Okay, so distance of rocket from Earth center is x, so it is x squared, and that's equal to force on rocket due to sun, which is g times mass of sun into mass of rocket divided by distance squared. So here distance will be r minus x, and we have square of that. Okay, so here we have some cancellations. So this thing g and g gets cancelled out, mass of rocket gets cancelled out, so we are left with mass of Earth and mass of sun over here. So let's write it on next page. All right, so we have mass of Earth, and I will take this mass of sun on left hand side, so divided by mass of sun, and it's equal to, I will take this x squared on the other side, so it goes in the numerator of right hand side, So it is x over r minus x, r minus x squared. Okay. So I wrote one capital X and one small x. It's one and the same thing. Okay. So I was using capital. Let's keep it capital. All right. So now let's substitute the values. So mass of Earth is given. So mass of Earth is 6 multiplied by 10 raised to 24. Mass of Sun is 2 multiplied by 10 raised to 30. So let's put the values. So 6 times 10 raised to 24 divided by 2 multiplied by 10 raised to 30, and that's equal to x divided by r minus x. I won't substitute r for now. Now 6 divided by 2 is 3. Then 10 raised to 30 divided by 10 raised to 24 is 10 raised to 6. So I will write 3 divided by 10 raised to 6 is equal to x divided by r minus x squared. And if I want x divided by r minus x, I will need to take square root. Okay, so I will take square root on both sides. So root 3, let's take square root. Okay, so after that it is root 3 in numerator and square root of 10 raised to 6 in denominator. And on right hand side we have x divided by r minus x. Okay, so it is root 3 divided by 10 raised to 3. So I will cross multiply. So 1000x equals to root 3 times r minus x. Okay, and I know the value of root 3, so it's actually beneficial to memorize these values, root 2, root 3. Okay, they come many times. All right, so it is root 3 times r minus x, and root 3 is 1.73. Okay, so I will substitute that value to 1.73. All right, then again we have to divide by this 1.73. So it is 1000 x divided by 1.73 equals to I'm sorry, r minus x. So now we need to calculate this. So I will just use my calculator. Okay, it's 1000 divided by 1.73. So it's 578 point something. So I will just use 578 times x equals to r minus x, and I will take this x on other side. So it becomes 9 because this x goes, okay, this minus x on left hand side becomes plus x. Okay, and therefore we have x equals to r divided by 579. So how much is r? R is 1.5. I'm sorry, it is 1.5 multiplied by 10 raised to 11 meters. So I will use this value 1.5 multiplied by 10 raised to 11 divided by 579, and once again I will use my calculator. So it is 1.5 1500 divided by 579. Okay, so it is 2.59. So x is roughly 2.59 multiplied by, it's 10 raised to meters. All right, so this is the answer. So have you got the answer? All right, so if my algebra is not my algebra, so if the values I put in the calculator and the answer I have got, if this is correct, this thing is correct, if these calculations are correct, then this must be correct. Okay. All right. Now let's move on to next problem. So next problem is, at what depth below the surface of Earth will the value of acceleration due to gravity become 90% of its value at the surface? Surface meaning Earth's surface. Okay. So let's find it out. At what depth below the surface of Earth the value of acceleration due to gravity becomes 90%. Okay. So this is simple problem. We have the simple formula for acceleration due to gravity at depth d. Acceleration due to gravity at depth d is g suffix d, and that's equal to acceleration due to gravity on Earth's surface multiplied by 1 minus d by r. Okay, so d is depth, r is radius of Earth. All right. So now it's given that g suffix d is 90% as that of g. So let's substitute that. So how do we write 90%? So it is 90 divided by 100 times g. This is 90%. Okay, equals to g multiplied by 1 minus d by r. Okay, so g and g gets cancelled. G and g gets cancelled out. So it is 90 by 100, or I can say it's 0.9. So it is 0.9 equals to 1 minus d by r. So which gives me, if I take d by r on left hand side and 0.9 on right hand side, so I get d by r equals to 1 minus 0.9, and that is 0.1. So answer is d equals to 0.1 r. Okay, so how much is r? R is 6,400 kilometers. So yeah, it is not asked in terms of r, so we have to substitute the value of r. R is 6,400 kilometers. The radius of Earth is 6,400 kilometers. So let's substitute that. So it is 0.1 multiplied by 6,400 kilometers. So that is 640 kilometers. Okay. So it was simple. So yes, it's eMath box. Yeah, hi, eMath box. All right. So is it clear? Okay. So then let's move on to another problem. Okay. So here we have two planets in circular orbits around a star, and they have speeds v and 2v. Okay. A, what is the ratio of orbital radii of planets? So we have to find out ratio of orbital radii, and what is the ratio of their periods. So there are two questions. All right, so here we need to remember some formulae. So what is formula for the speed of a satellite in an orbit? Okay, same formula will be speed of a planet in an orbit around sun or a star. Okay, so formula is square root of gm over r. Okay, so there are two planets. So let's suppose speed of first planet is v1 and its radius is r1. Speed of second planet is v2 and its radius is r2. Okay, so v2 equals to square root of gm or r2. So let's call this 1, this is 2, and let's divide 2 by 1. So we have v2 by v1, it's equal to square root of gm over r2, and dividing by gm or r1 is multiplied by its reciprocal. So let's multiply by r1 divided by gm. Okay, what is m? M is mass of the star, not the planet. Okay, so gm and gm gets cancelled out and we are left with square root of r1 over r2. Square root of r1 over r2. Okay, so here v2 is 2v and v1 is v. So v2 divided by v1 is 2, and if we square this, what do we get? We get r1 divided by r2 equals to 4, or r1 is to r2 is 4 is to 1. Okay, so this gives me r1 or r2 equals to 4, or r1 equals to 4 times r2. All right, so it was very simple problem. Okay, so then what is ratio of their periods? So this is again very simple. There is a relation between um, the time period and the radius. So if you remember, it is Kepler's third law. Okay, so we know that t square is directly proportional to r cube, or I can write t square equals to some constant multiplied by r cube. Okay, so I will write t square equals to some constant multiplied by r cube, and therefore now I can say that t2 equals to constant k times r2 cube. Okay, sorry, t2 square equals to constant k times r2 cube, and t1 square equals to same constant k times r1 cube. Okay, so k gets cancelled out, and again we are left with t2 by t1 square. So t2 by t1 square is equal to r2 by r1 cube. Let's add a page, and therefore if we take square root of both sides, so what do we get? T2 by T1, so T2 upon T1 equals to R2 divided by R1 raised to 3 by 2. Okay, and we already have R1 by R2 equals to 4, so R2 by R1 is 1 by 4, so it is 1 by 4 raised to 3 by 2. Okay, so 4 cube is 64, and square root of that is 8, I guess. So T2 by T1 is 1 over 8. Okay, yes, so this is the answer. Is this clear? This is very simple. All right, then let's move on to next problem. Okay, so next problem is, does the escape speed of a body from the earth depend on A, mass of a body, the location from where it is projected, then the direction of projection, and the height of location from where the body is launched. Okay, so does the escape speed of a body depend on all these things? So it does not depend on mass of the body. We can just write down the formula for escape speed. So escape speed ve equals to square root of 2 times gm over r. This is from earth's surface. Okay, so it does not depend on mass of body, it does not depend on the location, and it doesn't depend on the direction of projection. Okay, so considering that earth is a uniform sphere, the escape speed is, I guess, 11.2 kilometers per second. Okay, this is escape speed of a body from earth's surface. But does it depend on height? Of course it depends on height, because um, the acceleration due to gravity changes, okay, as we change the height of body above the earth's surface. All right, so acceleration due to gravity changes, so the gravitational force changes, and the binding energy, the energy required uh, to make a body escape from earth's gravitational bounds, it will also change. All right, so escape speed does depend on the height and not the other things. Now you might ask that the height of uh, body will be different on different parts on earth's surface. Okay, different parts of earth. So height on Himalaya and height on the sea level, it's not same. Okay, but that difference is very small compared to radius of earth, so we can neglect that almost. Okay, so this is the answer for this question. Hope it is correct, sorry, hope it is clear. Let's move on to next question. All right, so next question is, the escape speed of a projectile on earth's surface is 11.2 kilometers per second. A body is projected out with thrice this speed. Okay, what is speed of the body far away from the earth? Ignore the presence of sun and other planets. So it's given that escape speed of a body on earth's surface, it's 11.2 kilometers per second, and a body is projected, so v equals to 3 times of v, thrice this speed. Question is, what is the speed of body far away from earth? So let's suppose at infinity, okay, at infinite distance. So this is simple problem. It is based upon the law of conservation of energy. So we can say that sum of potential energy plus kinetic energy, I will write U and K, U for potential energy and K for kinetic energy. So U on earth, so bad, U on earth plus K at earth equals to U at infinity plus K at infinity. Okay, And we have found the formula for potential energy, which is minus of gmm over r, considering the potential energy at infinity is 0. Okay, it is some constant and we consider it to be 0. All right, so let's substitute that, plus here we'll have half of m times v at infinity squared. Okay, kinetic energy is half of mv squared. So u at earth is minus of g m over capital R, plus k on earth is half of m into v squared. Okay, now let's solve this. So we can substitute v equals to 3 times of v. All right, and if you remember, ve equals to square root of 2gm, 2 times gm over r. Let's add a slide. All right, so what will be v squared? So v squared equals to 2 times gm over r. So either I can substitute this v equals to 3 times v and then substitute v equals to square root of 2 times gm over r, or what we can do is, in place of the gm over r, we can substitute v squared. Okay, all right, sorry, half of v squared. So this gives me gm over r equals to half of v squared. And doing this will be beneficial because we are given that v equals to 11.2 kilometers per second. Okay, so everything will be in terms of v, and then we'll be able to find out v at infinity. Okay, so let's substitute that. So gm over r is half of v squared. Let's substitute in this equation. So we have m times minus of gm over r. So we have minus of m multiplied by half of v squared plus half of m times 3 times of v. Okay, v is 3 times of v, so 3 times of v squared equals to, here we have half of m into v at infinity squared, so half m v at infinity squared. Okay, we can multiply this whole equation by half, so we get minus, and we can cancel out m, m and m gets cancelled out. So we have v squared minus v squared plus 3 times v squared, so it is 9v squared equals to v at infinity squared. Okay, so we have multiplied by half, sorry, we have divided by half, and we have cancelled out m. Okay, or we can say we have cancelled out half m. So v at infinity squared will be 9 minus 1, that is 8v squared. V at infinity squared equals to 8v squared. If we take square root, we get v at infinity equals to, this is square root of 8 multiplied by ve. So 8 can be written as 4 times 2, square root of that, so it is square root of 4 multiplied by square root of 2, so it is 2 root 2 times ve, and we can substitute for root 2, so root 2 is 1.414. Okay, so I already told you that memorizing root 2 and root 3 is beneficial, they come in handy lot of times. Okay, so v at infinity is 2 times 2 point, sorry, 1.414 root 2 is 1.414. I will just use 1.41 multiplied by V is 11.2. Okay, so it is 11.2 times 2, that's 22.4. 22.4 multiplied by 1.41, that many kilometers per second. Okay, so you do that math. uh, just let's just add one page. What happened? Anyways, okay, so yes. Hi. Okay, Gangadharan is saying my name is Sahana. All right, so are you there, Gangadharan? I was solving this problem. Sorry, now Sahana. Your name is Sahana? Okay. All right. So now seems like we can't add another page. So okay. So V at infinity will be equal to what? It is 2.42, sorry, 2.82 multiplied by V. Okay, that is 11.2. And okay, Sahana. So you have been attending these classes since very long, and you told me today that your name is Sahana. Okay, anyways, so it is 2.82 multiplied by 11.2, that is 31.58. Okay, so V at infinity will be 31.58, and the answer is in kilometers per second. Okay, all right, so is this thing clear? Okay, then again let's move on to the next problem. Next problem is a rocket is launched vertically from the surface of Earth with an initial velocity equal to half the escape velocity. Okay, so initial velocity is half of escape velocity. Find the maximum height attained by it in terms of r, where r is radius of Earth. Okay, ignore atmospheric resistance. All right, so this question is also simple. A rocket is launched vertically from the surface of Earth with initial velocity v equals to half of the escape velocity, and we know the formula for escape velocity. It is square root of gm over, sorry, 2gm square root of 2gm over r. All right, so now what we can do is we can use the law of conservation of energy once again. So let's do that. So we have kinetic energy plus potential energy on Earth. So kinetic energy on Earth plus potential energy on Earth equals to kinetic energy at height h plus potential energy at height h. Alright, so now let's substitute kinetic energy is half of m into v squared. Potential energy is minus of gmm over r. Okay, so I will just write minus of gmm or capital R. So that is equal to kinetic energy at height h. So we are asked at what maximum height will the body reach, okay, the rocket reach. So the kinetic energy when it goes to maximum height will become 0. So this thing is 0 plus we have u at h. So it is minus of gmm over r plus h. Okay, so distance will become r plus h now. Okay, so let's substitute for this v. V is half of v, and now you can guess why I have written this formula. So it is half of m times v squared, which is square of this thing. So it is half of square root of gm 2 times gm or r squared. And that's equal to, okay, we still have minus of this gmm over r, and that's equal to minus of gmm over r plus h. Okay, all right, so now okay, so let's square this. So we have half of m times half of m times square of this thing. Square of half is 1 by 4. It is 1 by 4 multiplied by square root of 2 gm or r is just 2 gm or r. Okay, so it is 2 times gm over r. Then we have minus of gmm over r. So minus of gmm over r, and that's equal to minus of gmm over r plus h. So minus of gm capital M or multiplied by small m over r plus h. Okay, so it seems like we can cancel out gm and m everywhere. Then here we are left with 2 and 2 gets cancelled out. So it is 1 by 4r. It is 1 by 4 r minus 1 by r. Oh, it's 1 by 4 r in denominator minus 1 over r, that's equal to minus of 1 over r plus h. So we can reshuffle this. So what do we get? 1 over r plus h, we can just multiply with negative sign, is 1 over r minus 1 over 4r. So that is 3 by 4 r. And again we can take this 4r on left hand side and r plus h on right hand side. So 4 times r is equal to 3 times r plus h. So that is 3r plus 3h is 4r. So 4r equals to 3 times r plus 3 times h. So we can take this 3r on left hand side. So 4r minus 3r is r. So r equals to 3h. So this gives me r equals to 3h, and hence h equals to r by 3. Okay, so this is the answer. So at what maximum height the rocket can reach when it is fired with velocity equals to half of the escape velocity? It can go up to the height of r by 3, okay, in terms of radius of earth. So is it clear? Okay, it is Caleb P. Yeah, thanks Caleb. Is this thing clear? All right, let's move on to next problem. So yes, the escape velocity from the earth is v. What is escape velocity from a planet whose radius is twice that of earth and mean density is same as that of earth? Okay, so now escape velocity on earth is v, and we are asked what is escape velocity on a planet, some other planet. So let's suppose v, okay, v e suffix p is escape velocity on the planet, escape velocity on that planet, okay, on the planet. All right, so we know this formula for escape velocity, it is square root of 2 times gm per r. There is another formula, and that another formula is when you replace this gm by g times r squared, okay, you get that another formula. So it can be also written as square root of 2 times gr. Okay, if you substitute gm equals to gr squared or g equals to gm or r squared, okay, we can write it like this. So we had derived this another formula too. So now why I have done, why I am using this formula, it's because I know the formula for acceleration due to gravity in terms of the radius and mean density, okay, and that formula is 4 by 3 pi r rho g. Okay, so all of these things I am writing for earth. Okay, so we can substitute that over here and we get escape velocity on earth surface equals to square root of 2 times this 4 by 3. So 2 times 4 by 3 is 8 by 3, square root of 8 by 3 pi r rho g times this r. So I am substituting for g. All right, so it is 4 by 3 pi r rho g multiplied by r. So we have r times r, so it is r squared. So pi r squared rho into g. Okay, so we can take r outside, but for time being I will keep it like this only. So this is for earth, and what will be escape velocity for that planet? It will be equal to square root of 8 by 3 pi, in place of r it will be radius of that planet, okay, it's my p not rho, the radius of that planet squared, then rho for the planet, and g is same everywhere, so rho for the planet and g. If we are given that mean density is same as that of earth, so rho for planet is just equal to rho for earth, and its radius is twice, okay, So radius is twice. So let's substitute for that. So then it becomes square root of 8 by 3 pi into r for the planet is 2 times r for Earth, and we have square of that. Then rho is same, the mean density is same, and g is universal gravitational constant, so it is same everywhere. All right, so then we can take this 2r, sorry, it is 2 squared, that's 4, and we have square root, so we can take it outside, so it becomes 2. Okay, and I can rewrite this as, so what I will do is, uh, we have lack of space, I guess. Okay, I have another frame. Okay, so this is VEP and it's equal to, I can just take this 2 outside. Okay, it is 2 squared and its square root, so it is 2 times of square root of, we have 8 by 3, 8 by 3 pi r squared rho times g, and this is just escape velocity of on Earth. Okay, so this is just escape velocity on Earth, so this is 2 times of VE. All right, so escape velocity on Earth is VE, and escape velocity for that planet will be what? 2 times of VE. Okay, so is it clear? Yes, hi Shashikala. So V velocity of escape on the planet is 2 times of velocity of escape on Earth. All right, so is it clear? Okay, so let's move on to next problem. Two particles of masses m1 and m2 are initially at rest at infinite distance apart. So there are two particles, their masses are m1 and m2. They are initially at rest and distance between them is infinite. They begin to move towards each other due to gravitational attraction. So due to the gravitational force, first particle pulls on second particle pulls on first particle, and distance between them goes on decreasing. Okay, find the ratio of their accelerations and speeds when separation between them becomes r. All right, so let's solve this. So now when separation between them is r, the gravitational force of attraction between them will be gmm over r squared. Okay, so the gravitational force F suffix g is g times m1 into m2 over r squared. Okay, so this is force on first particle due to second particle, as well as force on second particle due to first particle. Okay, we know this is true from Newton's third law. So force on first particle due to second particle is this thing, and that is equal to force on second particle, so magnitude is same, due to the first particle. All right, so now what we can do is we can substitute F2 F12 and F21 equals to gmm or r squared, but we need not do that. We are asked what is ratio of their accelerations. Okay, so force on first particle can be written as mass of first particle multiplied by acceleration of first particle, and force on second particle can be written as mass of second particle multiplied by acceleration of second particle. Okay, so what is ratio of acceleration then? A1 by A2 is just equal to A2, sorry, M2 by M1. Ratio of accelerations A1 by A2 is uh, the inverse of ratio of masses M2 by M1. Okay, so is it clear? Yes. So this is part 1 of the problem. So okay, and then in part 2 we are asked what is ratio of their speeds. Okay, what is ratio of their speeds? So what I will do is, okay, how can we solve the ratio of speeds? It's simple. See, one way is you find out the speed. Okay, so you begin with both the particles start from rest, then uh, they come close to each other. So due to the mutual attraction, the gravitational force of attraction, so you find out the speed. And another way is just to use the law of conservation of in momentum. Okay, so we'll use law of conservation of momentum. So what was the momentum when they were at rest at infinity? It was zero. So I can just say the initial momentum equals to final momentum. So initial momentum was zero because both the particles were at rest. Okay, so it is zero, and therefore final momentum is m1 v1 plus m2 v2, and this is zero. So this gives us that m1 v1 equals to minus of m2 v2. Okay, that means they are moving in opposite direction. Okay, so m1 v1 equals to minus of m2 v2, but we don't want the direction, so we just want magnitude. All right, so I will just write this as, okay, so I will write it here because there is some issue, I can't add more slides. So I can just write in magnitude m1 v1 equals to m2 v2. Okay, so this is just magnitude. I just want magnitude of velocities. All right, so m1 times magnitude of v1 equals to m2 times magnitude of v2, because magnitude of velocity is speed, and therefore I get magnitude of v1 divided by magnitude of v2 is just equal to what? M2 over m1. Okay, so we can solve this problem in this simple way. So ratio of accelerations is also m2 by m1, and ratio of their speeds is also m2 by m1. Is it clear? Yes. All right, so now Is it clear? No, okay, Sahana. So some problems are from NCRT, not all of them. Some problems are from NCRT. All right, let's move on to the next problem. What is orbital radius of Earth satellite having a period of 1 hour? What is unreasonable about this result? Okay, so we have a formula for the orbital period. So T is equal to 2 pi into square root of r cube over gm, and we have to memorize this, unfortunately. Okay, so then we can square it, so we get t square equals to, because we want to find out the orbital radius, we want to find out r. Okay, so t squared equals to 4 pi squared to r cube over gm, and then this is just plug and play problem. So we get r cube equals to gm into t squared divided by, I'm just moving this gm and 4 pi square on other side, so this gm into t squared divided by 4 pi squared. All right, and I want r, so I will take cube root on both sides. So if you take cube root, it becomes raised to 1 by 3. Okay, so t equals to 2 pi square root of r cube by g divided by gm. Yes, the formula is correct. Then okay, so after that, what you have to do is you just have to substitute the values. So g is 6.67 multiplied by 10 raised to minus 11. Mass of Earth is 6 into 10 raised to 24. Time period is given, it is 1 hour. Okay, so if you substitute all of that, you will get the value of r. All right, so it is simple. Calculations are not simple, but it is just plug and play problem. So what is unreasonable about this result? You will get some result, and since this time period is very small, I guess the radius will be smaller than radius of Earth. Okay, so you just plug in the values and find out the answer. So unreasonable thing will be the radius of this orbit will be lesser than the radius of Earth, which cannot happen. Okay, a satellite cannot move from inside the Earth. Okay, it can't orbit inside Earth. Okay, so that's the unreasonable thing. All right, so this one is simple, and there is another problem. How will you weigh the sun? That is, estimate its mass. This is from NCRT, I guess. The mean radius of the Earth around Sun is 1.5 into 10 raised to 8 kilometers. So again, mean radius is given, and what else we know for Earth and Sun? So Earth orbits around Sun in 365 days. All right. So once again, we can use the same formula, that t squared, not t squared, t equals to 2 pi square root of r cube over gm, and we have taken its square also. So t square is 4 pi square multiplied by r cube over gm. T square equals to 4 pi squared into r cube over gm. So you want to find mass of sun. So here Earth orbits around sun. So formula for time period will be same as that of formula for time period of a satellite orbiting around sun on Earth. Okay, just mass of Earth will be replaced by what? Mass of sun. Okay, so it's the same formula, T equals to 2 pi square root of r cube by gm. And what is r? It is mean radius of earth around sun. So now if we substitute values, we will take mass of sun on left hand side, so it is 4 pi squared into r cube squared. But we can't put t equals to 365 days. We have to convert that into seconds. Okay, so t equals to 365 days. So that is 365 multiplied by 24 hours. So this thing multiplied by 60 minutes and again multiplied by 60 seconds. Okay, so we have to put this thing over here. So again there are lots of calculations, and r is what? R is 1.5 into 10 raised to, I guess, 8 kilometers, 10 raised to 8 in kilometers. So in meters it will be that thing multiplied by 10 raised to 3. So it is 10 raised to 11. So substitute this, substitute time period, just do calculations, and you will get mass of sun, and the answer will be mass of sun is equal to 2 multiplied by 10 raised to 30. Okay, it was given in some problem, in some earlier problem. So mass of sun yes, in first or second problem itself over here it is 2 into 10 raised to 30. Okay, so you will get 2 multiplied by 10 raised to 30 kgs. All right, so is this thing clear? Yes, these are just calculations. All right, so I will stop at this point, and tomorrow we will start with the next chapter, that is mechanical properties of solids. All right, so let us stop at this point. Bye everybody, good night.